I'm Jason Weston at Facebook AI Research in New York, actually, but we have another big group here in California. I also, want to apologize. I got pretty sick actually a day ago, and my throat got pretty sore. So if I'm not super loud, that's actually the reason. So I recovered enough to come here, but it may affect my voice. So so that's me, and I'm going to be talking today about some algorithms that we've developed at Facebook with Sumit Chopra and Antoine Borde as well, who work there. And they're called memory networks. And so they're kind of a variant of neural networks where obviously from the name you're allowed to have some large external memory which the neural network is going to be able to access, and it's going to be able to read and write to this memory in order to fulfill its function, whatever it's doing. So in particular, we've been focusing on the problem of question answering. So, given like first some kind of story or some kind of knowledge base is fed to the neural network. So this would be stored in its memory. And then given a question, it has to try and answer the question. So this is the point, where it can use its memory to sort of, try and learn where to access in the memory to read in order to answer the question. So like a really simple example would be like a factoid question, like where was Barack Obama born or something like this. So, you kind of need like some kind of memory to store all these facts, where all different people are born and, what's the capital of different countries and so on. So these are kind of traditional sort of information retrieval kind of way of using memory. And then another thing that motivated us was about reading stories, about reading comprehension. So there you kind of, imagine you're reading a novel or something like this. You also need a memory, right? To store, like, as you're reading a novel, you're remembering all the plot points, all the things that happen. And then you're given questions about the story, and you're trying to answer those. So there some slightly different things come into play when you're question answering, because you need to take into account more time order of the story, if you like, compared to these kind of sort of factoid questions which mostly don't change, like what's the capital of France. So for example, if you were asking where someone is, like a really stupid example, like someone's gone to school, and then in the evening they go to, I don't know, the cinema, and then there's a question, where is that person? That's going to be a different answer than if you asked the question earlier on, before they'd gone to the cinema, right? So you have these kind of facts that are actually kind of changing depending on the time point. So that's a slight sort of variation that you have to take into account kind of when you're reading a story. Anyway, these are the kind of motivations for these models that we came up with, but we think they have lots of other uses as well. So once you have this memory tied to a neural network, you can do lots of other things with it. Like maybe you could have a robot going through a maze and using its memory of the maze to help understand how to solve that problem, things like this. But we focus on more question answering rather than acting, which in that case the robot would be acting about moving around in a maze. So a lot of machine learning has been successful without really needing this memory component that we're going to talk about. So for example, a lot of what we call kind of low-level tasks, I mean they're still difficult, but things like object recognition that convolutional neural networks have been very successful at recently, they don't really require this memory. So in that case, you just take an image and you put it through your feed-forward neural network, and then you get a prediction out of like, you know, that's a kitchen, or that's a butterfly, or whatever, right? So you have those classes at the end of the neural network. So in that case, it's remembering what those objects are, but it's done basically sort of fried into the neural network parameters of the weights in the feed-forward network, right? Those are trained, and the memory is learnt through stochastic gradient descent, right? So through the learning of the gradient descent to optimize the error function, predicting the right classes, you're kind of memorizing what those classes look like. So that's a different kind of memory to sort of being told like a story, or, you know, like facts, and just sort of being able to just memorize those things like straight off, right? And just sort of store them in your memory, right? There, you don't have to necessarily do all this gradient descent to, like, you know, start off your weights at random and then slowly move them following the gradient to the right point to remember these facts. You might want something more like a RAM, right, where you can just kind of get that fact and write to it. So that's kind of the motivation for these models that I'm about to show you. Yeah, so I think I basically said it's on that slide. So yeah, you can have, so reading comprehension kind of problems might look like this. So this is a data set collected at Microsoft called MC Test. So they got human annotators to write these like little stories like this about James the Turtle, and then human annotators to write these questions and answers at the bottom here. So there's a little bit of a problem with trying to train a network off this data right now, that we just don't have really enough of it, like labeled. So this data set, for example, is like 660 stories in total. And if you look at those stories, you can see that there's going to be lots and lots of common sense reasoning that the network needs to learn to be able to answer these questions. And, you know, for going back to ImageNet, it wasn't, you know, we didn't really see good performance from neural networks relative to other models until we had like more like millions training examples, right? So there's a little bit of a lack of data in the question answering sort of field right now. So what we're going to do in our fast experiments is just make some very simple simulated data, more like from a text adventure game, and show that these models can work there. And when we do that, we can kind of understand what they do and what they cannot do in terms of being able to easily specify in the text adventure game different kinds of questions that we can ask. So that's what we're going to do first in terms of experiments. So we made this kind of very simple text adventure game. I don't know if you're familiar with those things back in the day, like Zork, and things like that, multi-user adventure games and stuff like that. So they had these kinds of instructions where you could go to a location, you could get an object, you can get an object from another object, like get the apple from the table. You can give an object to another person and drop an object in a location. And you can also look and ask for an inventory of what you're carrying and things like this. So what's good about running this kind of simulation and then generating text from it to make a story is that we're going to have the grounding to the actual simulation, right? So we're going to be able to generate labeled data and understand what the answers should be, because from the simulation we know where all the objects are located and all the people. So we made that kind of thing, very simple, but so we can run kind of just really simple simulations with this text adventure game. So you have something like this. So these are like in the command form that I just showed you. So Antoine go kitchen, Antoine get milk, Antoine go office, drop milk, Antoine go bathroom. And then you can ask, have a question answering setup within this simulation, such as where is the milk? And here the answer is the office. because Antoine, you can see Antoine got the milk and then he went to the office and then he dropped it, right? So presumably it's still there after he goes to the bathroom. So you can see that to even this very simple setup, you can make this kind of questions that are actually a little bit non-trivial to get the answer to, because you kind of have to understand, or the machine has to understand kind of what get, go, and drop kind of mean, right? So that it understands that Antoine got the milk and then he went to the office and then he dropped it, so he no longer has it when he goes to the bathroom, right? So somehow it starts to understand what these things actually mean if it's answering the questions correctly. So that's kind of in the simulation sort of command space. And then what you can do is try and make some simple grammar that converts that to something a little bit more like natural language. So here we did that with it's just a very simple piece of code basically that switches the word go to one of different 5 different synonyms for moving, like traveled or went and things like this. And so it looks a little bit more natural here. If you put a lot of time into that, then maybe you built a quite complex grammar. You could make this stuff look more and more like natural language. This would be the idea, so that eventually, hopefully, you got it to look basically more like this, right? Which is more like the real stories written by annotators. So that's the kind of goal, to do some experiments in this setup. So our first task, we just call it like the where is actor task. So it's just like how I showed you on the slide before. You would get a story, which is a sequence of these commands translated into something that looks more like natural language, followed by a question, like where is John? And then you're given the answer, which is the playground in this case. And you're given in the training set for a learning algorithm what we call supporting facts, which are the pieces of the story that are relevant to answering that question. So in this case, there's only one supporting fact. Okay, so this is kind of looks quite a lot like the basic factoid question answering sort of setup. But like I was showing you, like I was saying, with say, where was Barack Obama born? There you might need to find like this single supporting fact, basically, that gave you the answer. So yeah, we call this a strong supervision case, where you're basically given the supporting facts as well as the question answer pairs. And then you can imagine having something like 1,000 of these question answer pairs, say, for a training set with these different randomly generated stories, and then a test set of different stories. And in the test set, you're not given the supporting facts. You're just given questions, and the goal is to answer them. So that's the first task. And then the second task is a little bit harder, is the sort of requires 2 supporting facts, basically. So we have like questions like where is the football, or where was Bob before the kitchen. So here, like as I was saying before, the where is the football question requires both of these sentences as supporting facts. So, and you can see that basically some kind of algorithm that's going to answer this, kind of, if it's looking for supporting facts to be able to answer a question, it kind of needs to do them like iteratively, one after the other, because to answer, say this, where is the football, the first thing it's got to do is kind of find something that's been talking about the football, right? So that would be this one. So it finds that John picked up the football, but it's still not actually be able to get the answer from that, right? So it doesn't actually say which location the football is in. So now it needs to go off and find another supporting fact, given that it now knows that John has picked up the football, that gives more information. And this other one now it knows John has a football, it knows that John is in the playground from the first one, right? So it can find the second one conditional on the first one and the question to collect both of the supporting facts. So this is going to be kind of how the algorithm works, that we're in the memory networks algorithm. It's going to be finding these supporting facts sort of one after the other, and then each time it finds one, it's going to sort of condition on the ones it's found to find the next one, until it finds all the things it thinks are relevant to answer the question, and then it can produce an answer given the supporting facts. This is kind of the idea of what we're going to see. And similarly, I didn't put the supporting facts, but it's a question like this: where was Bob before the kitchen? You would need to find a supporting fact of, say, when he went to the kitchen, right, first, and then find the next supporting fact, the one before, where he was before the kitchen, right? So find that one and then find that one, which would presumably be the closest other time he moved, closest to the one where he went to the kitchen. So you can see how, again, some timing thing is going to come into play to answer those questions. So we didn't want to have just like all toy data, so we have done experiments also on kind of a bit more real question answering data. So we looked at this reverb dataset by Fader et al., which consists of 14 million statements which are extracted from the web, mined from ClueWeb. And they look like they're put into these subject relation object triples after they're extracted. So you can imagine like 14 million of these types of things. They're like very diverse, and they cover things like Milne authored Winnie the Pooh and like Sheep Be Afraid of Wolf, and some of them are just not true. They're just tons of stuff collected from the web, but those you can look at then as your memory. And you can try and answer questions using those as kind of supporting facts instead. So we're given only a very kind of weakly labeled question answer pairs to train on this, and also paraphrase data, which is basically says there are pairs of questions that are written in a slightly different way to each other that should have the same answer. So this is what was given in this data set. So you can say that that these two questions should have the same answer, but you don't actually know what the answer is. That's how it's set up. So so here's a couple of, for example, these two: who wrote the Winnie the Pooh books and who is Pooh's creator? They're both like paraphrases in that case, according to the data set. So that's the kind of the more real data set. So now to the finally to the models themselves. So I'm first going to describe at like a super high level, because we sort of see this as like a class of algorithms, and we think there's actually like a lot more to do in this area. So we've kind of implemented like basically the simplest things we can think of. And shown that they kind of work on this data I've been talking about, but I think there's like much more sophisticated things we can still build and solve more interesting problems. So at this very high level, we think this sort of class of algorithms consists of 4 components, and they kind of go in order. So the first is the I component. It's like the input feature map. So here you're given some input is coming in to the memory network. In our case, it's like a sentence. So you can think it's either a sentence that's one of the statements from the story, or it's a sentence that's a question. And in either case, you still, in this input component, what you're going to do is do some feature pre-processing effectively, right? So there you could, for example, do standard part of speech tagging or semantic role labeling or parsing or these kind of things to process the text and output some input feature representation to the next component, which I'm going to describe in a second. Or you could not do those things if you don't want to. You could just, you might be not really one of these NLP people that wants to do this kind of processing, and you want to do more like word embedding models, like word2vec and things like this. And in that case, you can just take the input and just turn it into word embeddings instead, if that's what you want to do. So we've left that kind of free. So in the next component, whichever you choose, in the G component, it's allowed to take that representation, the input representation you've built, and allow to update the RAM, the memory. So basically in this G stage, we call it generalization, you're allowed to write to the memory. So we called it G, well, partly because it spells out Igor, so we could get this guy, but also because at that time you could essentially do some kind of reasoning as you write to the memory. Like, so, for example, if you've got two sentences, like, I don't know, Brad Pitt is an actor, and then the second one is he starred in the movie Fury. So in the second one, you have a he, right? So you can perform some co-reference, if you like, and you could, instead of storing, say, he starred in Fury sort of in your memory, you might want to do that generalization where you work out the he is actually referring to Brad Pitt, and then store that in the memory instead, right? So you're kind of you can be doing some reasoning on the fly in your model to work out what you want to store in the memory. So we're not actually doing that in the model that we built, but I think it's a good idea to do that, and that's sort of what should be explored in the future. So what we're actually doing is more sort of in the next component. So in the O component, so if the G component is writing to the memory, so the O component is going to read from the memory. And here, when you're reading from the memory, you can also do some reasoning, right? So here, if you looked at the stories I was describing before, this is where you want to kind of find your relevant supporting facts, right? So as you read from the memory. So here, basically, we're going to do kind of the bulk of the work to be able to answer these questions in the model we implement. So the O component, after it's read from the memory, it's supposed to build an output representation. So this is also a feature representation, different from the input representation from I, but which is meant to represent all the features necessary to sort of answer a question successfully. Or, if you were using this not for question answering, but for, say, a robot acting, it would be all the features necessary to act well, right? And then in the final component, the R component, that's where you use this output features to actually make the final response. So in our case, that's outputting the answer. So, given that you knew, for example, how you wanted to answer a question, you can then, in the R component, kind of just phrase the answer sentence, how you want to present it to the person it's speaking to, for example. So that's a super high level set of models. So there's actually been a bunch of work just in the last couple of years where people are starting to get interested in memory and attention with models. So here I'm just mentioning a few of them. So the first one is RNN search, which is a model for machine translation from Joshua Bengier's group, Badeno et al. He's the first author. So that model works by having a source sentence coming in, which is going to be translated to another language, and as it's outputting the translation, it's going to try and do some attention over which part of the source sentence it's going to focus on as it's speaking. So, as it wants to translate, say, some word into French that's kind of, near the end of the sentence, it wants to do sort of attention on the end of the sentence in the original source language. So you can think of this as a kind of very simple, small memory that basically operates only over one sentence. But we can sort of see this basically as fitting into this memory network's basically class of models. It's just that in the experiments we're going to do, the memory isn't over one sentence, it's over many sentences, over a whole story. But otherwise, we're essentially doing this kind of attention thing, looking for the supporting facts. So there's also been other work by Alex Graves for generating sequences that also does attention, and particularly from DeepMind Group and Alex Graves recently, there's a neural Turing machine model which is also very similar to the ones I'm going to, well, similar in spirit that it uses memory, but the actual experiments they do are like totally different. So there they have a set of models which they show can just work on sequences. So they also consider artificial data, but not question answering data, but more like can they like copy sequences or sort numbers, and like very simple sort of sequence problems like that. But it's actually, you know, fairly impressive that those models can do those things. So to do that, you actually have to have, if you put their model into this framework, you actually have to have this more complex G function, basically. So when you write to the memory, so for example, to sort a set of a sequence of characters, you can imagine, you know, various sorting algorithms that have to, I mean, depending on the sorting algorithm, you have to write the stuff in a certain way so that you can read it off easily, right? So that you can sort it. So you can link those models to our one in that way. There's also a lot of earlier work. I mean, sort of neural networks spans back not the last few years, but you know, from a long time ago. And so when we put our memory networks paper on, like, we submitted it to a conference, iClear. There's one guy, Jürgen Schmidt-Huber, who's done a lot of work, in RNNs and many other areas of neural networks, especially in the 90s. He wrote this long public review saying you should cite all these things we've done from the 90s. So yeah, I think you know, there's lots of stuff from back then which is we need to kind of go back and study again now in the context of you know, the sort of new computational resources we have now, and data as well, hopefully. So yeah. So our first memory network implementation is going to be super simple. It has these I, G, O, and R components, but we kind of try and make them to be the, you know, the absolute essence, the simplest we can, to try and that still can give interesting results. So the I component, all we're going to do is take the input text and do nothing at all with it. We're just going to take it and we're going to keep it in like Word format. And in the G component, we're going to store in our memory. So our memory is just going to be a big array. We're going to store in the next slot that we know isn't filled yet, that text. Okay, so we're just going to store the story. So all the work, as I was saying, is going to be then in the O component, right? That's going to have to do all the reasoning. So now to answer one of these questions, like where is the milk, where is Antoine, or like, you know, where was Barack Obama born, we're going to have to do all of that in the O component when we're reading from the memory. Okay, and so the way we're going to do that in our first experiments is basically with just one or two iterations over the memory. So we call these also hops. So in the first hop, what we're going to do is we're going to take the input X and we're going to go over every memory location MI that's already filled. I mean, presumably we've still got a whole bunch of memory that we haven't actually filled yet. All the ones that are filled with story or knowledge, we're going to score them with a neural network, okay, that's going to do the matching between X and MI, and presumably, you know, going to tell us which ones are the good match, right? So the idea is to look for these supporting facts, okay? So that's the first loop, and then in the second loop, after we found the maximum scoring MI, so the best supporting fact from the first loop, we're going to have another little neural network that's going to be matching, again, all the possible candidate memories. So it's going to run through all the memories and match them, but now with not only with the input X, so the question, but also with the first supporting fact that we found on the first hop. Okay, so that's how we're going to be able to solve these kind of two-hop kind of things where we need to know that John picked up the football to find where John actually was.
What happens if you only have one, or you need 3 or 4, and you have millions of memories?
Two different questions. So in our first experiments, we basically always do 2. And then if you need 3, it's just going to fail. But obviously, you could see how to generalize this to 3 or 4. And we did that in our second paper, basically, which I'm not going to talk about. But the easiest way is simply to have a kind of a stop memory. So when you're scoring over all the memories, if there's this special stop memory, you also score that, and that gets a better score than any of the memories, then you stop, right? If you don't hit that one, then you do another loop and keep conditioning on more and more memories until you hit the stop memory. So that's one way you could sort of have an adaptive number of hops, and we've explored that. So the other question about going across all the memory. So yeah, if you've got something like 14 million facts, obviously you've got 14 million like scorings you have to do, and that's going to end up being too slow. So there we just look at basically traditional information retrieval tricks to do, for example, like hashing or inverted index, to basically try and cut down the set of candidates to a very small set in a sort of pre-filtering stage, and then only score those ones. So those are the things. But I mean, if you could try and sort of end-to-end train that thing at the same time, that would be nice. But at the moment, we haven't done that. Yeah. So that's the O stage, and then finally. So then, if you've only done 2 hops, you get this output representation, which is X, MI, and MJ, which are the 2 maximum scoring memories you found, the 2 supporting facts, right, from the memory. So this is your output representation. That goes into the R module. And now the R module is going to take that, and it's going to rank all possible responses. So here in the toy data, the answers are just single words. So that's nice and easy, because we can just go across our whole dictionary of possible words and score them with this thing as the input features. Okay. So now I just need to explain kind of what is actually this neural network model that's doing the matching between, say, this and this, or this and this, right? You could choose a lot of different things for that. I mean, you could choose like a support vector machine to do that if you wanted to. For us, we use embedding models. But
another question. So in this seminar, going through these facts, how do you handle it? That thing you are asking for changed, so you need to take that last fact into account.
What changed?
So, for example, if the question was like one of the facts was like John is in the kitchen, and then John is in the bathroom. And the question is, where is John?
Oh, yeah. Yeah. You need to take into account time, right?
So how do you
yeah.
have this model?
Yeah. So I haven't got to that yet, but I will. But basically, one way would be to have some kind of, so the memory MI here, when you express it in your matching function, you need some feature which represents time. So which the time is basically the index. Because we're storing them just, always like that. If you have a feature which is basically the index.
And like how the value is to boost the score for that particular.
Yeah, I mean, if, for example, it wanted to find the most recent one, then you could imagine that if you added, that index, it could, boost the ones that have a larger index, right? But if you're answering a question like, where was this one, where was Bob before the kitchen? It needs to do a little bit more, right? Because it needs to find the one that's most, in the second hop, the one that's the most recent thing that says where Bob is, but not more recent than that one. right? So it needs to do some little bit more complicated thing, but you can do that, you know, if you just put in these features and, you know, has some function of the features in the model, right? I am going to show actually a trick we do for that in a second. So first, some extensions. Yeah, so at the moment we've assumed that the model takes like sentences as input, but you could consider other variants, like it just has words come in as input. And if you did that, then you need to kind of do something a bit smarter in terms of what you write to the memory, because you don't just want to write all the words to the memory. It'd be nice if you could, you know, segment out sentences or useful chunks of sentences and write those pieces sort of to the memory. So that's sort of one extension you could look at. Another extension is, instead of just ranking single words in the final response module, you could try and output a full sentence, right? And that's where you could use a recurrent neural network, like they're doing in, say, the machine translation work or so on that I mentioned. Then this was my answer to Richard's question about if the memory is huge, so you could try and do some hashing or bucketing or something like this to try and only score some of the memories. I've actually got some experiments on that in a second. Finally, if the memory got full, then you'd need to start doing some forgetting, right, to free up some RAM. So I haven't actually explored that at all yet. That's kind of open problem, but you could imagine some ways of doing it, right? Like if you think some part of your memory had never been accessed, or, you know, it didn't ever look useful to answer any questions, or some things like that, some kind of utility function for the memory, and then try and erase the ones that look like they don't have much utility, something like that. But yeah, so onto the matching function. So here, yeah, we're using basically embedding model. So we use a bag of words on both sides. So both sides of this matching function, where I mean the two arguments. So for example, if you're matching where is the football as the question to one of the possible memories, John picked up the football. So this would be a good match in this case, right? Obviously, modulo the time aspect, which I'm going to talk about in a second. But so to do this, we have this matching function here. So Q is the question, and D is like one of these possible memories, and the U matrix is the set of all your word embeddings. Okay, so if you haven't seen this, you've probably all seen this kind of thing before, but so Q then is basically of dimension, you know, the size of the dictionary. Actually, in our case, the size of the dictionary times 3, because we're going to take basically all the possible words in the dictionary, we're going to prefix them with one of these 3 prefixes, Q colon, D colon, or Q2 colon. So the reason why is basically because we want to represent differently the question, the first supporting fact and the second supporting fact, so that they have different word embeddings. And this is so that kind of the model knows which one it is, and it works, I mean, basically it works better if you do it this way. I mean, so yeah, so that means we're going to have the whole dictionary of words, you know, times 3. So let's say the dictionary is, you know, 1,000 words or something. We're going to have a 3,000 dimensional vector Q and a 3,000 dimensional vector D. And then U is going to be, you know, like 3,000 by, say, 50. So we're going to have a 50-dimensional, you know, word embedding for every one of our 3,000 symbols. So this is the model, and then so to featureize that matching function, we're just going to say turn the left-hand side into, you know, all the words basically, but put the Q colon in front to say they're from the question, and for the right-hand side, all these D colon. Yes.
Sorry for the embedding prefixes. It totally seemed like Yeah, I understand why you would want different embeddings, but you might also want the embeddings to be related, like Q colon football and B colon football. Is there any enforcement of that, or is that all learned from scratch?
It's all learned from scratch, but you could imagine having some regularizer that tried to, say, push them to be similar or something like this, but we didn't do it. Yeah, sorry, there is actually an extra complication here that I didn't describe. We also added this possible features QD match that say when there's an exact word match between like the two arguments, so the left hand side and the right hand side. So in this case, like football appears in both the left and right hand side, right? So you can add this extra special word QD match football as well. And if you add these extra symbols, you thus need to extend your dictionary to have those in the dictionary as well. The reason why they might be a good idea is because when you're in an embedding space that you've basically pushed everything down into a 50-dimensional space, when you multiply by this matrix U, you can't necessarily recall exact word matches anymore between the two sides, right? So that's when this QD match feature will still give you that exact word match. This is actually going to end up useful as well to deal with unknown words. So we have some experiments where, I'll show you later, but so in our stories, we've never seen, say, any characters from Lord of the Rings. So imagine now we see, in our story, Boromir went to the kitchen. I guess he must go to the kitchen sometimes. Then, we won't have a word embedding for that word Boromir. Right, so because we haven't ever seen it before, but these, you could have a special QD match feature that basically says there is some match between them, but I don't know what it is. We're going to use that later, but it's kind of an extra sort of sugar on top, really. But yeah, so those are the features in the first hop, and then after you found that first supporting fact. Let's supposing that where is the football? John picked up the football was the first supporting fact, and that was found. Now you want to score a second supporting fact, and you use it's conditional both on the question and that first supporting fact, right? So now the left-hand side features are both the Q colon words from the question and these Q2 colon words from the first supporting fact. So that's why we have these three dictionaries. And then the right-hand side features are still D colon, wherever John is in the playground. And possibly still these Q2D match or QD match features as well, although those are more optional. Yeah, so that's basically what the thing looks like, and then basically you want this thing so that after you've done the embedding of the question into the 50-dimensional space and the dot product with the 50-dimensional embedding of the memory, that dot product, if it's a supporting fact, should be a large dot product, right? And if it's not a supporting fact, it should be a smaller dot product. So then the objective function basically ends up looking like this. This is for like the whole model, like both optimizing the O component that finds the supporting facts and the R component that produces the response. So basically the first line is for finding the first supporting fact, the second line for the second supporting fact, and the third line for finding the response. Right. So this is a sort of a classic hinge loss margin, ranking loss function that basically says that, so this matching function SO that takes in the left-hand side, right-hand side, the X, the question, and the true supporting fact M01 here, that should have a margin gamma, be a margin gamma larger than the match with any other fact F bar, basically. So which is basically anything else from your memory. And then the same thing on the second line, except you have the supporting facts from the first hop. So MO1 is now in the first argument of the function. So it's conditional with the question, and the second fact is the thing that you're matching with. And then the final line takes all three, the two supporting facts and the question, and it's doing the matching function then against the possible response word. So all the words in your dictionary. Yeah.
So, what's the advantage of using this ranking clause here
compared to
like log loss that is coded by?
Yeah, there's other losses you can use,
So
and
why use one?
actually they perform pretty similarly. Why not this one? I could say, really. So I like using this one. I've basically done a lot of stuff in information retrieval where you use these ranking losses, and they seem really natural because you're ranking the documents, right?
I'm just like, whether it is sensible, like, to actually say, to consider it like, okay, it didn't produce correct answer, but it was like, I don't know, fifth best answer. Whether that's a sensible way of evaluating.
Oh, but this is how you evaluate in training, right? Not
Yeah.
in, yeah. Well, you're trying to get the right answers to the top, right? I mean, you have to choose some way of doing that. You either do it with probability, say, it has to have the highest probability, or it has to have the highest score, or, there are all different ways of trying to do the same thing. I've actually tried with, like, NLL criterion, so more like probability way, and is very similar results. So
But this one should be faster, right? Because you don't have to go through all.
yeah, that's the nice thing about this. If you've got like a ton of memories, so you can train this. So this sum here, where you're saying all f not equal to MO1, you can subsample the negatives. But you can do that with other criteria as well. I mean, so people have also done that with NLL criterion, but that's typically how I train it. I would pick like a few random negatives and only use those ones on each stochastic gradient step, so each step isn't like really slow.
So when you have the SO and SR functions there, the scoring functions, that's the dot product, right?
Yeah, that was the basically embedding with the word embeddings and then doing a dot product, yeah.
So do you do that on a per word basis and then sum across all the words in the sentence? Or?
Yeah, so that's exactly what you're doing when you do this. So this thing Q is going to be let's see. It's going to be like a vector that's a dimensionality of like 3 times the dictionary, right? So if you're ignoring the those QD match features, it's kind of complicate things. So and it's kind of like it's a vector of like many zeros, right? And some ones. So where they're basically going to tell you like which words are switched on, right? In the so so let's say where. So this is like the word where, right? Here, and this is the word is here, like this, right? So you're defining basically the sparse vector with just 1, 2, 3, 4, 5 non-zeros, right, in Q. So then when you multiply that thing by U, right? So then you've got your what is it, like 3,000 dimensional vector with only your 5 ones with a 3,000 by 50, right? What you're doing is you're pulling out the word vectors for each of those 5 words, right? And then summing them.
Yeah.
So it's exactly, taking the word, it's exactly taking the word embeddings of each of these words and summing them, and that's your representation of the question. And so that's this bit, the QUT, and then you're doing exactly the same on the other side. You have the representation of the memory, you get those word embeddings, you sum them, so now, the bag of words is sort of bag of word embeddings, if you like, is like a sum of the embeddings from each of the two sides. Those are the two 50-dimensional vectors you've got, and now you do a dot product. And that dot product is the similarity now between the two sides, and we want it to be large basically when there's a good match. Yeah. So where was I? Yeah, so now, about time. So your question is about time. It's a bit behind on this. So you can add this absolute time features, or you can do some extra trick that we tried. I'm going to go quickly on it because it's just an extra trick, really. That what you could do is, if you want to encode relative time instead of absolute time, you could compare triples of things instead of pairs of things. So instead of taking the question and one memory, you could take the question and two possible memories. And now when you do that, you can actually represent the relative time between the two memories. You can have a feature that says memory D happens before memory D prime, or after it, or the other way around. So we tried that basically, and that worked quite nicely, because relative time is kind of more what you're looking for than absolute time. We just kind of want to know, did this thing happen after this thing in the story or not? So then if you do that, you can make a binary feature that does that. So that's just kind of an extra trick that you can use, and it changes the objective function a bit, but it's basically the same thing, except now, because you're comparing triples of things, you want to avoid comparing all possible pairs of memories against the question, because that's too slow. So what we do is we just do the kind of really simple tournament. You take all the possible memories, you start at the top, and you say, okay, the first one's the winner. Now, current winner. Now take the second one, and the first two memories versus the question, so that's a triple, they're going to battle against each other. And when you go through this function that matches all three, Q, D, and D prime, we want that the value of that to be less than 0 if D is the winner, and greater than 0 if D prime is the winner. So we keep the winner from the first two, depending whether it's less or greater than 0 in the matching function. Then we go to the third one, and we battle the third one with the winner from the first two, and so on. And in that way, you can just linearly go down all the memories, keeping the winner. It's the same cost as before, but now you're allowed to encode these relative time features, which are kind of handy. So that's basically an extra trick you can do. Yeah, so that brings us basically to some experiments. So the first experiments I'm showing are on the kind of that real data. Yeah.
But that relies that the function satisfies triangular inequality, right?
It satisfies what?
It means to satisfy triangular inequality.
Oh.
Because if you put circle and that question and that matching function and answer, these three answers are better in circular order.
Kind of, yeah. You actually, because we're not comparing all the pairs, you only need that the winner can beat any other memory.
Yeah, but
that's all you actually need.
If there was that circle, it just doesn't get it right.
Yeah, it's not necessarily going to work, but neither is the absolute time either. So, yeah. Yeah, so on the real data set, so that's the one with the 40 million statements, this Milne authored Winnie the Pooh kind of stuff. Yeah, okay.
So when you take the second memory, that's independent of what you chose in the first memory, right? When you choose the outputs, that's independent. It's three independent. You're training 3 networks, one for...
Oh, for the response, you mean?
Yeah. Because it's a pretty strong assumption that you have, this is the first supporting fact, this is the second supporting fact, right? That doesn't happen in the real world. And it doesn't seem like a huge extension to just train directly from the answer. right? Like, did you ever try training from the answer, making the
Without any supporting
yeah,
facts.
just making them like
Yeah, so we call that the weakly supervised case, and we have studied it. So I'm not going to describe it here, but yeah, basically what you have to do is replace all these max functions over the memories, which I've shown with like a softmax. And if you do that, it's kind of easier to back propagate all the way through the network, basically, because then you get the gradients. And then, you don't necessarily need like the supporting facts, basically the supervision on the latent variables, if you like. And it can work. It doesn't work quite as well, but it does work.
how much work?
It's on these tasks I'm going to show it works pretty much as well, actually. But there's some other tasks. So I'm not showing those, but we've gone off with our text adventure game and tried to build lots and lots of tasks. We built like 20 tasks now, and we're failing on kind of like 4 of them, basically, even in the supervised case. And in the weakly supervised case, I think we're failing on more. I don't remember, maybe 8 or something like that. It's kind of, but the actual numbers, like depends what you call fail. So fail for us was if you were bigger than 5% error. But I mean, if you look at the actual mean error, they're not that far from each other. So okay, try and get through this slide. It's the large data set, and it's much simpler than like the simulated stories, in the sense that you don't actually need these hops. You can just like find the first supporting fact and it works. So you only need k equals 1 hops. We did in these experiments 128 dimensional word embeddings, but I mean that's kind of you get good results basically if you do 64 or 256 or whatever as well. So here the time features aren't necessary either, because it's just basically finding these factoid kind of answers. So performance in terms of F1 score, we're comparing with this basically the original model. So this is the Fader et al. Model. So large is better. And so this is basically our memory network model here. Is basically real similar to something else that we worked on before with Antoine Board at Facebook. And it's better than the original model. And when we add these extra QD match features that I was showing in the earlier slides, we call them bag of words features, you can get some boost. But generally, the story is it kind of works on this kind of problems. It scales to these problems, except for the cost of going through like the 14 million facts, right? You actually have to run the matching function over all these 14 million facts, and that's not good. So then that's why we explored some kind of ways to speed that up. So we took 2 possible ways. One is like a classic like inverted index way, where you just take all the words in the question, and then you take only the possible memories that share at least one of those words. You can also use some stop words that are too frequent, like the, and say, okay, I'm not going to look those ones up, right? So that's kind of a classic thing. So we call that word hash, and then we can compare the performance of the embedding model, or the embedding model with the QD match bag of words thing with the word hash. It's a bit worse, but it's like way faster. It's like 1,000 times faster. And then we have another way of hashing instead, was we took the embedding space, so the word embeddings that we learn, and we run k-means in that embedding space, so the 128 dimensional embedding space. And we do that with, what do we do that with? Like 1,000 clusters. And so now we're going to find from the question, we're going to take all the words in the question and find all the memories that live in the same clusters as the words in the question. Okay, so that's not quite as fast now. That's only 80 times faster than the original. Still a lot faster, but the loss in performance is like negligible then. So, you know, basically the story there is there should be some ways to speed it up, like, you know, with some sort of classic ways to cut down the search space over the memories with, you know, to try and just find that a pre-filtering that finds the sort of relevant ones. I guess this one's a bit more than a pre-filtering because we actually used the embedding space that we learned to find the good clustering. So it's a little bit smarter, but yeah. So yeah, so that was the hashing. Excuse me. So now to the simulation experiments. So here, what did we do? We took 10,000 sentences, and we took like what we called two different difficulty levels. I think I missed saying that back here. Yeah, that basically that we can control the difficulty of a question by how far away the supporting facts are from the answer. So we call it like a difficulty of 1 if there's like the supporting fact is literally like only 1 sentence away, and a difficulty of 5 if it can be, you know, like 5 sentences away. So that's these two difficulty levels, and then these are the two tasks, the actor and the actor plus object, and we compare to like a standard recurrent neural network that's basically just reading the story up until the point that it gets the question, then it has to produce a symbol which would be the answer.
Okay, just to like go back to the cluster, you said you used k equal 1,000.
Mm-hmm.
Did you like do any like silhouette score on the clusters, or like any way to like see if there's like, it seems like you didn't really get that much drop in performance, which means that maybe the clusters are completely like you know, completely separate, like they're really good clusters. I don't know if like you.
I mean, I definitely looked. I looked at the words like that were in the same cluster as each other. So, because, you know, I'm using the word embeddings to cluster, and then I can look at the words in the same cluster, and they looked like really nice. I mean, they looked all semantically related.
Do they intuitional how like 1,000 clusters like can suffice to cluster like?
I don't know. I mean, I think the reason why so this data set is kind of simple in the sense that the reason why the inverted index is probably dropping performance is because it's like losing synonyms and things like this. Like, you know, it was like, I mean, spiders instead of spider, or some more, you know, complex, you know, black widow instead of spider. I don't know. So basically, if it gets those, it can keep the performance. That's basically, I think, what's happening. So the recurrent neural network is compared against the memory network with the k equals 1 hops or k equals 2 hops, and then either with the time features or without the time features. Basically, the 2 hops are necessary. So this is in terms of error rate. So you want like 0% basically. So on the actor plus object task, you need 2 supporting facts. We sort of, you know, by design, we built it that way. So without the k equals 2, you don't get everything right. With k equals 2 and the time features, then it can answer these questions correctly. And with only one k equals 1, it can only solve the first task as long as it has the time features. The RNN, on the other hand, basically can only solve the actor task when difficulty is 1, because it basically doesn't have this capability of like having a memory. So that unless the supporting facts happen like just before the question, it's forgotten them if they're 5 statements ago. So that's basically the problem. So while an RNN is like great for things like machine translation, where you just go from, you know, English sentence to French sentence, as soon as you've got like many sentences, you need something else. Basically, you need some memory or attention mechanism. So after we've done that, you know, you can see these little stories and, you know, see like answers to the stories, and, you know, they're pretty simple, but we want to get those basically closer to the real reading comprehension kind of stories. So we also did a sort of proof of principle of having like a full RNN producing the response module rather than just a single word output, but with a simple grammar. So then you could get like things like this that it outputs as answers. Oh, and in this case we also looked at segmenting the inputs into sentences as we go. So we learn we have a segmenter in the I module. So again, more as a proof of principle that you could have this more sort of realistic looking setting and it still kind of works. So yeah, as I was mentioning, we also did some tricks to deal with new words. This is like the first sentence where Boromir ever appears in Lord of the Rings. So to deal with that, we made this special context dictionary that basically, the way like a language model tries to learn about a word, right, is the words around it, like the two words to the left and the two words to the right. So, if you don't know this word Boromir, you kind of look around at its context to try and understand it. So we wanted to do this all within the same model, the same memory network model. So we do that with these special features. So we don't have like a word embedding for Boromir, but what we can have is like this special unknown word, but to the left is the word then. So like then is to the left of Boromir, and goes to is to the right. So we have this special unknown goes is to the right, and unknown to is to the right. So we basically can represent a missing word using these special context dictionary words. And the idea is then we could train our model, in the training set, we actually have all the words, we know them, but we kind of do this dropout trick where we pretend we might not know a word during training so that we're prepared basically at test time for this thing to happen. So what we do is sometimes during training we pretend we don't know a word. We pretend we don't know the word kitchen. So instead we represent it with these features to the left and right of it instead, and that way we're going to train these embeddings to deal well with the case when that word is missing and unknown. So that's kind of an extra trick that we added. And then when we do that, we could at training time not have any of these Lord of the Ring words seen, but at test time it can deal with them by looking at their context to the left and right. So given a story like this, it can answer these things correctly. It's just with the same training from the text adventure game that we had before. So then we can also do some stuff like take the Reverb 40 million facts data set and our toys, text adventure game data set, and kind of make an ensemble of the two models. And so given a little story, we could have questions that might be answered from the story or might be answered from your kind of large knowledge base of facts. So it doesn't always work very well, but so here it's like, where is the milk? It's in the office from the story, but then where does milk come from? Milk come from cow. This is kind of stuff is extracted from Reverb, and some of them are pretty stupid. Yeah, like what does milk taste? Yeah, milk tastes like milk, but milk go coffee. But you can imagine this kind of like Eliza 2015 basically, that you could sort of make a really dumb chatbot with this kind of thing.
The reverb is mostly triples, right? How do you get the sentences?
Yeah, so that is actually a triple. I just cut off the commas, and the hyphens. So that's basically it. So things to do next are, and a couple of these things we have done, so I'm going to explain, is make the simulation much more complex and try and move it further and further towards the real world. So like computer games have basically become more and more realistic as we go on, like the graphics are becoming more and more crazy. Maybe you could do the same with like text, right? And so make this thing like really good, generate really good training data that might actually be useful then in the real world. So that's one thing to do. So, and then, when the data's more complex, we need to make the model potentially more complex to be able to solve those problems. So like dealing with more than 2 supporting facts, dealing with word order, because we just had a bag of words model in the matching function, these kind of things, you know. So that's sort of our first attempt to do that is on archive, but I'm not going to describe it. It was basically, like I was saying, we've built like 20 tasks now instead of just the 2 tasks that test different things like co-reference resolution and like pathfinding. Can you find your way from the kitchen to the bathroom by going through the hallway, given, you know, a description of how you get from one place to another, and all these different kinds of tasks. And we can make many more, and hopefully we can get people interested in making more, actually. And then the other thing that you asked over there is like get rid of the supervision of the supporting facts. So to do that weekly supervised. So we have another paper on archive that does that. But the model really looks pretty much exactly the same. It's just, yeah, swap max for softmax and back propagate through. That's basically it. And then there's lots of stuff we haven't done yet. So we'd like it to be able to ask you questions rather than just answer questions and respond to statements and perform actions. And, you know, then you could actually have more like a close to a full dialogue engine, something like that. Okay.
All right, let's give thanks to Jason. So I hope, no, it's all right. I hope you're able to understand most of what he's talking about. You know, we covered word vector embeddings, we covered recurrent neural networks, covered the max margin objective function. So hopefully, you know, you can see that this class, while maybe in the beginning was hard, like now you're actually really up to speed to a lot of what's currently going on in deep learning research. In the next lecture, we'll actually cover the last major model family that you know is kind of important, namely convolutional neural networks. And then the week after that, we'll have you know, some tricks for GPU implementations and more efficient sort of distributed computing for training larger models. Just organizationally, really quick, for feedback on your proposal, please come to my office hour on Wednesday. And because the office hour on Wednesday, you know, you'll have 2 more days until you need to submit your milestone. So the milestone deadline will be Wednesday at midnight. And there's also a question if you ran your baseline experiments. Basically, the main you know, hope here is that you can run your baseline experiments on your final data set of your project. And if you did so, indicate this in your write-up too, as well as in the final project write-up. Are there any organizational questions? Yes?
When are your office hours on Wednesday?
You can check it on the website. All right. Right after class. All right. See you next Wednesday.